interact with him so that he feels that he is in a lively, vibrant classroom session, okay? Thank you very much, Professor Jonas, for being with us, and the stage is yours now. Thank you.
Thank you very much for this very kind introduction. Very nice to be here. I always like being at the National Center for Physics and in Islamabad, and nice to see you. I'm going to indeed teach you about statistics, and I'm going to teach it a little bit having myself in mind. It's not always the best way of teaching, but in this case I think it will be okay because I didn't know anything about statistics when I started my PhD. I hated it at school, and then I realized how essential it is to understand actually any kind of science, because the essence of science, of physics in particular, is that we make predictions and we make measurements, and statistics is a thing that takes one to the other. So we are quantitative science. So that actually statistics comes in many, many places in physics. Certainly in quantum mechanics, as you know, quantum mechanics is intrinsically a probabilistic theory, so statistics comes in there in a very fundamental way, actually, an individual particle level way. In thermodynamics, the modern formulation of thermodynamics is called statistical mechanics, and statistics is essential for that as well, and in the interpretation of data. And that's what I'll focus on in these lectures. So I will not talk about quantum mechanics or thermodynamics, although I love them both, but this is about interpretation of data. And that applies then to all of physics and any other quantitative science. And there are plenty of examples of this having gone wrong. This is a famous discovery of the cascade CC, 3.5 GeV by the Senlex experiment. So they think that is a signal and this is the background. And they saw it again a few years later. But then many experiments that had high statistics, I should have seen it there, but there's nothing there, really. And then that is the Higgs discovery in 1995 at around 110 GeV or so. But it's not the real Higgs, of course, as we all know. It was discovered at the LHC a few years later. And that one is a real one. At both CMS and Atlas. I know that the National Center of Physics is involved heavily in the LHC, and especially CMS. And this is a discovery at the top. Again, this is the in 1985, and that is the true discovery 11 years later. So what I'm trying to say is there are lots and lots of false discoveries. Maybe I'm overdoing it. This is a pentaquark discovery. Again, this was actually quite interesting because that hung around for a while, but then everybody looked for it, and you could. There was a time that a particle data group entry that said, well, clearly there has been some observation of the pentaquark, but it could never be repeated, so it's obviously not there. And then much later, 11 years later, LHC did discover the pentaquark. The pentaquark, you know of mesons, you know of baryons, and usually mesons are made from quark and antiquark, baryons of 3 quarks. These are made from 5 quarks. And they're completely allowed, but we had never seen it before. This is the earlier mentioned Psi-CC discovery at LHCb, and there's an animation that I hope will work. So this is how we take the data. And the thing I want you to look at this and ask yourself, at which point are you convinced that there's really a peak here? That it's real, it's not some fake fluctuation. And one important aspect of statistics and the interpretation of data is to quantify that sort of gut feeling and make it quantifiable in terms of probabilities and numbers. So how likely, assuming there's no psi double C, how likely it is that I see a peak like this just as a statistical fluctuation? And I would say very unlikely at the end, but quite likely still. I wouldn't say anything there. And at some point you say, oh, that's probably real. So we want to quantify this. We want to be scientific about it, not just have that. So, the problem, I mean, there are many of these false discoveries. Although we're getting, I think, much better with statistics, and I hope and I have the impression there'll be few of those in the future. And the problem is that nature doesn't allow us a direct view of the fundamental parameters of our model. If you ever had an undergraduate experiment measuring, say, the gravitational constant G or something like this, you will never get the exact value. Actually, we don't know the exact value because there are always some uncertainties in these measurements. They might come because a truck goes past your high precision, low vibration setup, or the electricity supply fluctuates a bit, all sorts of things. So if you say that we measure that the Lagrangian of the standard model is this kind of thing, that's the thing that John Ellis will talk about, I suspect. What an experiment like CMS gives us is at best this. Probably only a little section of this because they actually got only the low energy part of it. So but yes, so and statistics is a way of interpreting a picture like this and say, not only, it's not that we can take the blur away necessarily, sometimes we can. More often, it's important just to understand how little or how much we know. What can we say with confidence? What aspects of the standard model do we know? Or the measurements that we take, and what do we know? So, I just quickly skip through because I've just said all of this. Just the last point that I hope you're all psyched up now. You want to do statistics in order to not discover some false CC or some other thing that doesn't exist. And I do hope genuinely that you will discover something new and maybe even something completely unexpected. Something real. So let's start with something real. It doesn't have to be new, but real would be good. And for your master's or your PhD, what you will be doing is you will be looking, most of you, at interpreting a lot of data, especially if it's an experimental one. If it's a theoretical one, often actually that comes in as well. It might be simulated data, but data nonetheless. And you will deal with a few basic distributions, especially Gaussian or some binomial, and maybe a few others, and I'll introduce you to those, because they're important. You'll deal with error estimates and error matrices, I'll introduce you to those. And you'll measure parameters doing likelihood fits and chi-square fits, and you do a lot of those, and we'll definitely cover that. We'll cover that next week, though. We're going to get one lecture. And for that, you will need to learn how to translate the physics. What do I mean with the physics? Well, the mass of the Higgs is 125 GeV, that's the physics theory. How does that result in a mass distribution of my detector? You need to be able to parameterize that in terms of that mass of the Higgs into probability density functions that you can then fit to the data. And you will want to know what's the uncertainty on the mass of the Higgs? How likely am I really to have seen the Higgs at all? This is this famous 5 sigma business. We'll get into that at the end of this program. I made some material for you. I'll bring it back as it becomes relevant. This is just an overview. There's a problem sheet. I will not be collecting problem sheets. You don't have to answer it. I encourage you to have a look at it because it really helps to think about the problems that this will solve you, because it will help it lodge into your brain. So have a look at the problem sheet, see whether you can answer the problems. I'll be happy to assist you or give you answer questions. And I will reveal the answers at the end, but try it without the answers first. And you can get that here. And then there are lots of, I wrote quite a lot of code, so this is one of these things that we don't need that yet. I'll point you to this particular one. And this we'll do that at the end of the lecture. We'll do that also early next week. And this is the entire set of code. So that's why that might also be interesting. That's quite a lot of Jupyter notebooks for those of you who are interested in this. This will be online, so you can just click on these. But this is also QR code. Before I continue, who of you has got a phone with them? A smartphone? Very good. Who doesn't? Okay. But if you have a smartphone, we'll try to bring it. It's quite useful in these lectures because I will ask you to answer some questions with your smartphone if you can. So,
but I'm not sure if there is a coverage for the data here.
Oh, there might not be. We'll try. We'll try. We'll see how far we get. We'll see. It might not work. Okay. So this is my roadmap for these lectures. I first cover describing the data itself and the most basic properties. So what do I see, if you like, and then what do I expect? This is about probabilities, probability distributions, probability density functions, and the central limit theorem. And I think I actually might swap this around and put the central limit theorem already here as the first part of this. And then we compare the two. So we have data, we have a theory, we fit the theory to the data, and then answer two questions. What are the theory parameters? And is the theory compatible with the data? That's what we want to know. So today we start with describing data, and I actually will be very quick about displaying data. These are bar charts, these are histograms, and I assume you know what these are. So I'm going to actually skip through this because I want to get ahead. And then this is I go a bit further now as we can in this lecture. These are my these are books I recommend, and I was delighted to learn yesterday that the authors of these actually come to this school every few years, which is great. So this is Roger Barlow. This is, I think, the best of them. If you only buy one, then it's this one. And what I like about it is that it takes you up really from the very beginning. It doesn't assume anything, or any statistics knowledge, but it takes you far enough that it will be your friend throughout your PhD. So this book is really good. Then Louis Lines, also very good. That focuses more on specific problems for particle physics. So I think it's a good book to have in addition. And then Frederick James, Statistical Methods in Experimental Physics. This is a bit of a monster. So this is not a book you want to, unless you know a lot about statistics already, this is not a book to get introduced to the topic. But it's very nice to look up things that are a bit beyond the other books. So really a lot is there, a lot of sophisticated material. And if you have a specific problem where you need a more sophisticated method, if you like, or you want to know a bit more the philosophical details, this is really, the practical ones, this is really very good as well. So these are the three I have anyway. I use them all. So now we come to the bit of describing data. And describing data, I've skipped a bit on how to make a plot, but I hope you will be able to figure that out yourself. If not, we can go do that again. But let's see, we are able to make plots. And the question I asked, the first question I asked, if I had to represent my data with one single number, what would I pick? And you all have heard about the mean, this kind of thing, that's what you would want, right? But here for this, I encourage you not to think too much about what would the mean of this distribution be or some other quantity, but I want you to look at this distribution, which happens to be the annual income distribution in the United States in 2006. Why do I pick this? There are so many other countries and so many other income distributions. I like the format of this plot. So that's why I stuck with this. And the income distributions, by the way, look very similar in most countries. They always have sort of this bulky bit here in the beginning, and then it tails out. And then sort of, I don't know, Jeff Bezos is somewhere in the mountains there. And I want you to think for a moment, look at this distribution, think, if I had to represent this as one number that sort of represents the income in the United States in 2006, which one would that be? Which one do you think conveys best this distribution? Think about it, and then we'll do science by voting. Well, I need to set this up a little bit. So, and what I'm going to do is I'm going to take these lines like this. I'll take it in the middle of the distribution, which is 240, so it's about here, it's the middle of the distribution. And I'm going to ask you whether you want the number, this representative number, this kind of mean, also average, to be to the left or the right of the line. And because left or right is a difficult concept, because it's different for me standing here than for you, I'm just going to point. So, and you have to vote. Do you want this to be on this side or on this side? So, this side, please vote. Okay. This side. All right. This side. This side. Okay, so you want this side. Very good. That, I think, makes sense. So I split this now again in half. And this, by the way, is a numerical method that's quite often used in order to find some number when you don't really have a more sophisticated way of doing it. You just split the interval and split and split. That is surprisingly efficient because in only 10 steps I will have reduced the width of the interval by a factor of 1,000. Because 2 to the power of 10 is 1. It's more than 1,000. So we do the same thing. So the question is about here or here. Who wants the representative number to be here? 1, 2. Okay. 3. Who wants it to be here? 1, 2, 3, 4, 5. Okay, the majority is here. Very good. So I'll split this one again. So we've put that here. Now I think, yeah, okay. So now we have 2 left. Now we all have 2. This one or this one, and this one. These have it, I think. We put it here, but it was a bit trickier, I think. So now I need my third line for the first time. So we put it here. So now between these two, this one, okay, and this one. I think that's a little bit, this is tricky. This one, and this one. I think this one has it. This one has it, so we put it in here. Okay, I do the last one I do. Maybe I'm overdoing it, doesn't matter. This one or this one, so this one, and this one. The split. I think it's split more or less evenly, so I just leave it where it is and say in the middle it is. So this is our vote. So I'll copy this one. This is our vote. Let's see how this compares to various kinds of means, which I have introduced you to. So let's have a quick look. There are many kinds of means or medians or representative numbers. One quite popular one, or an easy one, is a mode. That's just the win with the highest number of events in it. Clearly not very useful here. Then there's a median. That is where you have as many incidents above and below. That can be quite useful. And certainly is one of the best ones if you don't really have data that have a number like this one does, the income. But if you only have a ranking without a number, which can be the case, then this one is very good. And then there's a mean, which is the arithmetic mean. You all know how to calculate it. You sum up all the numbers and divide it by the number of entries. So let's see where ours is. So I'll paste now your vote into it, and your vote is here. So the vote, the number that you think is the most representative of this distribution is closer to the median than the mean, although most of the time we use a mean. But I can assure you that the Office for National Statistics in the UK, and I think most other offices of statistics, they use for income distribution indeed the median, because it is a more representative number. So you agree with the UK Office for National Statistics and most others, I think, on how average incomes are reported. And the reason is that Jeff Bezos out here skews the distribution, but is clearly a lot in the mean, because he has a significant impact on the sum of all incomes. So he skims off quite a lot, but that doesn't really affect the income of most people. So the median is not sensitive to that. It doesn't matter how far away he is, and is therefore a more representative number. And so it can be quite good for distributions that have very long tails, and income distributions typically do. So that was that. Any questions about that? Good. So that's where we are. Okay, so Having said this, most of the time, for most distributions, we will use the mean, the arithmetic mean in particular. So this number, the sum divided by the number of entries. And the motivation behind that is, above all, its nice mathematical properties. And we'll come to what these nice mathematical properties are later. But that's one of the biggest benefits of using that. And other central values exist. By the way, why did I do this exercise? I didn't do it mainly to introduce a median. It's a complicated way of doing it. The motivation behind this was, and that is true for many parts of statistics and actually for many parts of anything. Think about what you want to get out, what the meaning of the number is that you get. Don't just blindly apply it. It's, at the end of the day, you want to represent something that has substance and meaning, and therefore I want you to think about first here about what the meaning of the number is, and then which number, which mathematical process actually represents that meaning best. So think about the meaning of things. Don't just follow the rules. Okay, the mean is clearly not the only number that matters in order to describe distributions. These two distributions have the same mean, but they have different widths. Here I put resistance in ohm at the axis, so you could imagine that you get some resistors that you buy in the shop, and you get the high quality ones that have 100 ohms written on them, and they will have a distribution that's quite narrow, around 100 ohms, and then you get the low quality ones that have 100 ohms written on them, and they get maybe a distribution like this. It was one of my very boring undergraduate experiments to measure the resistance of high and low quality resistors and make a distribution like that. Amusingly, what you get is that the high quality one looks like this, and the low quality one doesn't look like this. It looks like this, and then it goes down, and it goes up again. I leave you to interpret these results. But, okay, I'll tell you. So the manufacturer produces this distribution, and then selects these to sell at a higher price, and these to sell at a lower price. But okay, we ignore that, and we assume that we have these two. And so, questions of how do you represent this fact that some of them are further away from the mean on average than the others? And one thing you could do is calculate the total difference from the mean, and that would be foolish, because that is, by our definition of the mean, and I encourage you to try this out, that's always zero. So that number doesn't mean anything. And that's because you have positive and negative results that just cancel each other out. What you want is something that's always positive. So what you do is, there's a sum sign missing here. So you want to have the sum of the distance of my data points from the mean squared, and then divide that by n. So that is basically the average, or there's so many mistakes in this. That's shocking. I did this last night, this slide. I improved it, I thought. And that's what you get if you do something last night. So that's, quickly fix this. So let's do this. Very good. Fix it. So that's the true meaning of this expression. That's called the variance, and it gives you the average distance squared from the mean. The disadvantage of the variance is, by the way, this is a calculational trick. This is the same, gives you the same result. You can calculate it as the average of x squared minus the average of x then squared. And the reason why this is a useful calculational trick is that you, if you calculate it with a computer, if you do this, you have one loop that calculates the mean first, and then you have another loop that calculates the variance. While here, you can do it in one single loop where you calculate the mean and calculate the mean of the square, and then you can use this expression to calculate the variance. So it's a bit more efficient. and I encourage you to verify this. I think I might have somewhere in the slides actually the calculation, but I'm not going to go through it here, because we have a lack of time. Now, the standard deviation is simply the square root of this variance. Why do I introduce this? Well, the variance, imagine we have something, some measurement in meters, say. The variance will be meters squared. I would like to have my measure of the width of the distribution in terms of actually the same units as my distribution itself. So that's why I take the square root. Why do I even have the variance then? Is it more than just a calculational tool? Well, the variance, like the arithmetic mean, the variance has very nice computational properties, and we'll come to those again later on. So the variance is good for calculations. The square root of the variance, which is the standard deviation, that is good for meaningful numbers. They give you a typical deviation that you have from your mean. And this typical deviation, often this is used as an error or something like that. We will use it as an error, indeed. But you should not forget that this is one standard deviation away from the mean. That is what you typically expect. So you should never worry if it's a little bit more than one standard deviation from the mean, or maybe even two. That's completely fine. This is all within what you would. It doesn't have to be all within less than the standard deviation at all. We'll quantify that later. Any questions? So far, so good, right? A bit of a tour de force. I mean, it's things that the idea I have, by the way, just if you know, I've thought about this. I think much of this will be familiar, but it's good to have a reminder. That's why I'm doing it sort of a bit quick. But if it's too quick, please tell me, and I'll slow down. I'm in no rush. So let me know. Yes, please.
So I've had this question for a while now, ever since I was in college. Okay, so statistician.
Just a second, please. So that other can also benefit from whatever you're asking. Come on.
It's a temporary solution.
I have quite a volume.
So.
Thank you. So the question was that statisticians usually work in arbitrary terms. Your outlier doesn't always have to be 1.5 times the interquartile range or something. It can be 2 times or 3 times. However, when we are talking about standard deviations, when you said that, okay, if you take the mean from if you take the mean of the differences, that will always give you 0. Why is it that you always take the square of the differences to calculate the standard deviation? And I know that when you take the fourth power, it gives you a completely different quantity, and that's meaningful too. However, why is it that statisticians chose and knew that this was going to be a more meaningful quantity, the standard deviation?
That's a completely sensible question. And there's some arbitrariness in this, I think. And there are other measures of the width of the distribution and how far away you are from it. For example, a little bit like the arithmetic mean, this thing here, just to emphasize how right you are, this thing is quite sensitive to outliers, because imagine you have something that's a bit further away than typically, that really blows up this number, because it comes in as a square here. So it's very sensitive to outliers. That might be fine. Maybe if you understand your distribution, you want these outliers maybe to have a big effect. But in some circumstances, for example, when it comes to track fitting and things like that, this might not be what you want, because the outlier is some noise or something that you don't want to affect your track direction too much. So if you want to have a distribution that's less sensitive to outliers, one way is not to take the square, but just the magnitude, and that's them up. The reason statisticians like the square, and I like the square, is the nice mathematical properties. It is, and we'll come to what these are, I think today even. That was my aim, that's why I skipped a little bit in the beginning. So my aim is that we'll come at least, the first part of the explanation, why the variance is so good, will come at the end of today's lecture or early in the lecture next week. But there is a reason, but the reason is really its nice properties. And that has to do with, if you combine distributions, variances add up. That's the biggest motivation for using variances.
So a really short follow-up question. How do you, all of you guys agree on that, if it's so arbitrary?
No, but it isn't so arbitrary. We agreed on that because of the nice mathematical distribution properties.
Okay.
That is, so it's not that arbitrary. But there are other measures of width, and they are in use. But why variance is preferred is not arbitrary. That is its mathematical properties. It behaves nicely. And you will see what I mean with this later. But it's not arbitrary.
And it's also visible from there, because if it's the square of if you just go over there, just the next slide. So you take the square and then the mean, and then you subtract the average of the square. That makes it positive. Otherwise, it's the square root of it, and it does not make sense at all.
Yes. So this positive is certainly one big advantage, but you could make other positive numbers out of it. But this is one that it's very nice. We'll see why it's nice today. Before we do this, we quickly do consider two multi-parameter distributions, because hardly ever in particle physics do we measure only one single value of something. We measure, for example, if we measure momentum, we typically measure x, y, and z component of the momentum, or the transverse momentum, and the total momentum, and eta, and the energy, and the standard deviation that the detector expects on your energy measurement. That's also a measurement in a sense. All sorts of measurements come in. How do we describe multi-parameter distributions? Of course, we can, for each parameter, tell you the standard deviation and the mean. But how do we show the correlation between parameters? So some parameters will be correlated. For example, in this audience, I would assume that the height and the weight of people is correlated, but it's not the same. But on average, taller people will be heavier, although there might be some very slim tall people that are lighter than some slightly wider short people. That all exists, but on average, the taller people will be heavier. So there will be some correlation between height and mass of humans. While I think there will probably be zero correlation between height and your score in your last exam. I think there's no correlation. We know that short people are as smart as tall people. The covariance is a parameter that's meant to capture this. And there's again an average, as you can see, and it's the average of this product of so parameter 1, the difference of parameter 1 from its mean, times the difference of parameter 2 from its mean, parameter 1 upon x and parameter 2 upon y. And this, let's all see how this works. Let us assume that these things are, we have two uncorrelated parameters. Then the probability that this is a positive number, bigger than its mean, and the probability that this is a positive number is as big as the probability that this is positive and this is negative, or the other way around. Basically, the probability that they have the same sign, these two, is the same as that they have opposite signs, because they are completely uncorrelated. So you will have a sum of a bunch of positive and negative numbers, and on average, it turns out this sum will be zero, if they are uncorrelated. For every real measurement, of course, it will deviate slightly from zero, but for theoretical distributions of uncorrelated parameters, this will be zero. While if this one and this one are correlated, then if this is a positive number, this one is a bit higher, and this is then this is also more likely to be a positive number. So this product is positive. And similarly, if this one is a bit lower, gives a negative number, and this one is a bit lower, and it's mean negative number, then this is also a positive number. So if you have a high correlation, you'll get a positive sign. So this is one correlation. The covariance works. The covariance, again, is a number with units, with the units of these numbers. So for the first example, it would have been meter kilogram, for example. But I might also want to measure that in feet stones or so. How does this translate? This is the calculation trick for this. The mean of the product minus the product of the means. And in order to make this easier to interpret, we introduce a correlation coefficient where I divide this covariance by the standard deviations of these two distributions. And that takes out the units, and also it makes sure that you get a number that always varies between minus 1 and 1. It's 0 for uncorrelated, an uncorrelated situation, and it's 1 for perfect correlation. The proof that it's 1 for perfect correlation is that if I put the covariance of the parameter in itself is just the variance, and then the product of the two standard deviations also just the variance of the same parameter, so that gives you 1. And then gives you a more meaningful quantity. And it's a little bit like with the variance and the standard deviation. The covariance is the one that is good for calculation. Covariance matrices are easy to deal with by comparison to the correlation coefficient. And the correlation coefficient is the one that gives you some meaning. And so we use both. And your fitter, Minity will give you actually a full matrix of correlation coefficients and covariances. So this is how these look like. So I generated random numbers, each of them Gaussian distributed, but I put in some correlation. But the first one I didn't put a correlation in, and the correlation coefficient is 0, so this is just a blob. And then I increase the correlation coefficient slowly, and you can see how this becomes more and more close to a straight line, and this is a correlation coefficient of 1. That means the two variables are the same. And that is why when your fitter gives you a correlation coefficient that is 1 or close to 1, that's often an indication that it struggles, because it means that you put two parameters in, but they mean the same thing. And then the fitter often struggles. It's a bit like saying x plus y is 5. Fit me that, well, there's an infinite number of solutions. Right? Or x minus y, in this case, it would be x minus 5. And of course, you can have negative correlation coefficients and just swaps this from going upwards to going downwards. And you can make plots like this yourself, exactly. So there's, in the uploaded version, you can just click this link that takes you directly to some Python code that makes plots like this. If you want to play around with this. Yes, please.
Sir, this type of correlation coefficients usually measure the linear correlation, right? And these are also like parametric, like they assume some assumptions about the parameter population.
They don't assume anything. The question is how meaningful they are if it's not linear, but they don't assume anything. You can just calculate it from any distribution. Talking about the meaning of these distributions, if two parameters are correlated, they might have something to do with each other. That's an interesting observation. But let's hit this. But statistics doesn't tell you actually what causes what, or whether there is really a cause between the two. So, for example, it rained earlier tonight or this morning, and there's a strong correlation between rain and wet roads. But although we know which causes which, the correlation coefficient doesn't tell you whether the rain causes the roads to be wet or whether the wet roads causes it to rain. There's also a correlation between wet roads and people running around with wet hair, but neither causes the other, but they're correlated because they have a common cause. So correlations are meaningful, but be careful in their interpretation. For example, this is the number of lemons imported to the United States from Mexico, and this is the total United States highway fatality rates. And this implies that the more lemons were imported, the fewer fatalities you had. So import lemons in order to reduce road deaths. I have a few other ones. Internet Explorer causes murder. So this is the use of Internet Explorer. It's a Microsoft product. It doesn't exist anymore for a good reason.
Causes murder. But
it seems to have prevented murder because the murder rate went down at the same time. By the way, this also gives you an indication of how maybe not to, but how to exaggerate effects in data, and that might not be the best thing to do in a scientific study, because this doesn't end with 0. This is quite a narrow range. So only plotting this narrow range exaggerates this downward trend quite a bit. And then one of my favorite is that this is the number of pirates in this Caribbean area, Northern Sudan. The number of pirates estimated, and this is the global average temperature. So clearly, the lack of pirates, so these here the numbers go down, the lack of pirates causes global warming. There are lots of these, so my encouragement to you is to write down 100 times, correlation is not causation. Once I've had this in a lecture and somebody else has said, it is meaningless, why do you use it? It's not meaningless, you just have to put some effort into the interpretation, that's all. Correlation can still be meaningless, it can hint you towards a causal relationship, but once you see the hint of a causal relationship, you need to investigate it and see whether there really is one. Alright. So, I have a summary on representing data. Do I have another sort of 20 minutes or 15?
10 minutes.
10 minutes, okay, that's after 20. Okay, maybe we'll see how we fare with this. I skipped the histograms in order to have these last extra 10 minutes. We did central values, usually the arithmetic mean, and I told you it has nice mathematical properties, and the nice property I'm going to investigate further is that if the mean of the sum is the sum of the means, which is a nice, this is really the nice bit of it. And then we used, we investigated width, and we decided that standard deviation is a good measure of width, the variance is the square of that. That's the thing we calculate first. And that also, again, we'll come to that in a moment, has this nice property. If you have the variance of the sum of two random variables is the sum of the variances, as these two variables are correlated. That's why we use the variance. This is really, I think that's the main reason. It gives you a parameterization of the width, and it has this very nice property. And then we looked at covariance and correlation. And this is, I did my homework. So I hope you will too. I'll check that in the next lecture. All right. So I'm wondering what will happen now. I'm not sure. I'll have 10 minutes, and just because I move on, although we only have 10 minutes, it doesn't matter. It's necessary to postpone this. Any questions to what we've done up to this point, actually? I was very pleased. I got some questions already. Yes.
Just a second.
Correct. So, as Sarvati usually asks, why only Monte Carlo? Why not Markov chain Monte Carlo? Just because Monte Carlo, as of my knowledge, that Monte Carlo relies on repeated random sampling to obtain a result, whereas Markov chain is a sequence of steps in which the next step or state is being determined on the current state. So in the combination, Markov chain Monte Carlo is a computational algorithm that uses random sampling to approximate the solution of a mathematical or statistical problem. So why only Monte Carlo? Why not Markov chain Monte Carlo?
I completely agree with you. Markov chain Monte Carlo is great. So there's no reason why we use normal Monte Carlo. Any questions maybe related directly to the topic? Yes.
Yeah, you can take this one. Don't disturb maybe him.
Excellent. Does it work now? Yes.
Now it's
Yeah, it works.
it works now.
So you were talking about like correlation and covariance between two variables. Now, what if one of those variables is categorical? What then?
Yeah, then it doesn't work. This needs numbers.
Okay.
Yeah.
सवाल समझाओगे?
All right. Thank you very much for these wonderful questions. Now I'll move on, using my last 2 minutes to introduce a new topic, which is not the thing that you normally do in a lecture, but you will see why I do this, especially if your phones don't. Do your phones have internet connection here? No. Some do, some don't. Okay, so
They all have the cellular data for the WhatsApp, but they don't want to use the same data for this one.
that's okay. Okay, that's fine. So you'll see how we.
आप लोगों में cellular data है?
सर है क्या चलता नहीं है
सबके पास है मेरे ख्याल है. Why don't you respond? Come on.
सर मूवी चल रही है सर
जिनके पास है वो तो कर सकते हैं, लेकिन for those all of who have, let's say, euphone or the jazz, they can respond right away rather than just waiting for it.
Sorry about that. Does anybody know which band that is?
हमारे ज़माने का नहीं है सर.
No? Well, it shows my age. That was sort of quite in vogue when I went to the UK first in 1996 or something, a bit later, before you were born. So, okay, you don't know what that is? I quite like it. It's called Blur. And that is the topic that I want to introduce. It is the blur that I mentioned earlier. This is nature. This is our picture of it. And that blur tends to be Gaussian. And the big question is, why is that the case? Why is the blur that we get, why is that Gaussian? And that is, well, this is a Gaussian. This is a Gaussian distribution. So a Gaussian distribution has a mean, and it has a standard deviation. And the standard deviation goes from here to here. And famously, so this area covers about 68%. That's how Gaussian looks like. You will probably have seen it, maybe called a bell curve or something like that. This is me with Gauss in Göttingen. Göttingen is a friend of mine lives there, and there are these lines. And here, it's good to see that magnetic. And this is Gauss again, this is sine terms. And on money that doesn't exist anymore, that is pre-Euro. But it was considered important enough that this curve and the formula for it actually was on the money in Germany. So, and the Gaussian is important because of the central limit theorem, and this is the central limit theorem. So, take a random variable y, and that random variable is a sum of some other random variables that are called x with an index. So each of these x is a random variable, and they're independent of each other. That's an important part of this. And each of these x has a mean. These means are very different, and it also has a standard deviation and a variance. This is the standard deviation. Then, that is the, and then that also explains why mean and standard deviation are so good. Y has, I call it expectation value. I often use expectation value instead of mean for theoretical distributions. Same thing, so the mean that is the sum of the means of the other variables. It has a variance that is the sum of the variance of the other variables. So the variances add up. Importantly, this means that the standard deviations do not add up, right? The standard deviations add up. It's the variance that add up, and then if you want to use a new standard deviation, you have to take the scale of these, the sum of the variances. And then the most magical thing that whatever the distributions of these x parameters, and it really doesn't matter, I will prove that to you, well, in a very experimental physicist way, the distribution of y becomes Gaussian as we get more and more random variables that we add up. And that's why this is so important, for example, when it comes to estimating errors. Errors or uncertainties of your measurement, they come from all sorts of sources, but usually many of them. When there's a truck going past your lab, there's a phone mast that interferes with your electricity, there's some thermal fluctuating, there are many different independent causes. Each of them causes the measured value to fluctuate around the true one in a different way, and we have no idea in what way. But with this, we know that the result of that is most likely Gaussian, as long as you have enough of those different variables, and that's the magic of this. So out of basically complete ignorance, we don't know the individual distributions, we actually get something that we can understand. This is quite a magic thing. That's why the central limit theorem is made. So, what I plan to do, and that I will still do, although we will not do this at the end of this lecture, we introduce this new problem, I will ask you to roll dice. These are my dice. You will each get dice. You'll roll these dice, and submit results. And I will ask you to roll a die once, submit the result, to roll the die twice or 2 dice, submit the sum, and then to roll 10 dice and submit the sum of that. That's your task. And there will be a prize for the largest number of entries. So I hope you use it several times, because we said this works for n going to infinity. Although there are many of you, you're not infinite. So do it many times and let's see how this looks like. So, well actually this is wrong again, I'm being unfair. Yes, no, actually this is what I want. So the largest number of entries wins. There's a second one where you can guess or predict the result. And if you look at the definition of the central limit theorem, you should be able to tell me the result of what the mean and the standard deviation of each of these distributions is. Well, for the first distribution, you will need to calculate the standard deviation of the result of rolling a single die. That might require a little bit of thinking. I might help you with that. And then for the others, it follows from the central limit theorem. So these are the 2 things I want you to do, and we'll need them, especially this one, we will need for the first lecture next week that I'll give. So I really need you to go somewhere where you have decent internet access, roll some dice, and submit the results. You look at me as if it was a scary task. It's easy. Might be only to do. I'll tell you how to do it. This is how the interface will look like to scale less. I can just open link. That's where it is. Name. My name is Jonas. And then I'll roll a die. I got a 2. You see how it works? Right. I rolled 2 dice. I got 4 and 4, which is 8. And then I rolled 10 dice. Oh, 1, 2, 3, 4, 5, 8, 10. And that's of course a bit harder, but I think you can do it. This is 7, 17, 27, 37. That's 37. And I submit this, and the result has been recorded. That's great. And then I can have a look at the responses. Oh, some people have already, very good. I see that I'm not the only one. Ikra, you're a star. Whoever's Ikra. Ikra, are you here? You're a star, Ikra. Fantastic. So we have Ikra in the lead. The largest number of submissions will win, and we'll look at the score sheet when we start the next lecture, and then we will look at, of course, at how the distribution will look like. So I shall see you next week. Thank you very much.
Questions or comments? Please do this exercise with Jonas so that it's fun doing it. It's very wonderful. But if you do have questions or anything that you want to ask in person, he will be around during the tea, so feel free to approach him. And by the way, you can, all of you must have studied the quantum mechanics. So the take-home exercise will be just the variance that he calculates and the square root of the variance. Take the free particle, calculate the change in the momentum, the change in x, and then take the product. It should be of the order of h car. That's exactly what he has explained with the free particle and the product of the variance, which is the square root of uncertainty, the width of the resolution. Okay? Do that. It's a basic first chapter problem from Griffiths, particle physics or quantum mechanics. Thank you very much, Professor Jonas.
Thank you very much, and thank you to all of you, but especially Ikra and Syed Hadali for already starting this exercise.
Thank you.